So, in this session of waves in space-time and propagation, we are recapitulating the geometrical aspects of the wave propagation in space-time. And what we've figured out that there exist two kinds of transformations to go from one particular frame of reference to the other when there is a relative velocity between them v. And these two transformations of Lorentz are, one is boost and the other one is rotation. And we have shown that how to move from these infinitesimal transformations to finite transformations to get what we are otherwise familiar with in the Lorentz transformation equations. So, what we have discussed so far in the context of this transformation come under the category that is called OPLT. The O is orthogonal proper Lorentz transformation. As it stands, the Lorentz transformation can be distinctly classified into 4 subgroups, and only one of the subgroup has identity element with it. That is what is a OPLT, and that has the two transformations we have discussed during in the course of this lecture. So, let us try to see that if there is something more that is left. Okay. So, to see that, the starting point, the good starting point is a relation 13 that we have come across time and again, that relates the two transformation matrices with the Minkowski metric, and in general it is a matrix equation, and if we take a determinant, then what we get is determinant of this matrix square is equal to 1. Okay. So, we start from equation 13 and land up getting equation 35, and it tells us that the determined lambda matrix is a non-singular matrix. If lambda exists, then lambda inverse also exists, and what that means is if one lambda happens to be a Lorentz transformation matrix, then its inverse also is a Lorentz transformation matrix. That is the upshot of this particular equation. The other upshot of this equation is the magnitude of this quantity that we have defined by determinant of lambda, and the magnitude can be either +1 or -1. When the magnitude of the determinant is +1, this is called proper Lorentz transformation, and when it is -1, it is improper Lorentz transformation. So, that is the first classification. The next classification comes by looking at the sign of lambda 0 0. If you equate the left hand side and the right hand side of equation 13, which is a matrix equation, then we note that the 0 0 element of these two sides gives rise to equation number 38, which equates lambda 0 0 square equal to 1 plus the 3 perfect squares added together. Those are the elements of the Lorentz transformation matrix lambda mu nu. You know that if we have perfect squares, then and if they are real number, then the minimum value that can take is 0 and their maximum value can be anything. So, if you look at this equation, the conclusion that we can come is the minimum value of lambda 0 0 square should be either 1 or greater than 1. And that tells us that lambda 0 0 can be either greater than 1 or it can be less than 1, or greater than or equal to 1 or less than equal to 1. So, now if we take these two conditions and do a little bit of permutation and combination, then we see we can have lambda determinant of lambda plus 1 with these two other conditions. Those we have defined as orthochronous and antichronous, depending on whether lambda 0 0 is greater than or equal to 1 or less than or equal to 1 minus 1. And so, we get L arrow up plus and L arrow down plus. And if we take the two other values of lambda 0 0, then we get lambda arrow up minus and lambda arrow down minus. As we said, or as I said already before, that lambda arrow, L arrow up and plus sign is what is called the orthochronous proper Lorentz transformation. So, there exists space-time transformations. Those go by the name space inversion or parity transformation, and the other one that is called the time reversal transformation, and their structure is given by P equal to minus 1 plus 1 plus 1 plus 1 as the diagonal terms of a 4 by 4 matrix, or T matrix equal to plus 1 plus 1 plus 1 and minus 1. Same for a 4 by 4 matrix. These two conventions of P and T that I have defined here are based on the Minkowski matrix signature. If the signature is plus 2, this is what we get. And we can take a product of these two things together, two matrices together, to generate what is usually called the total inversion transformation, or PT, that gives by minus 1, minus 1, minus 1 and minus 1. And what is interesting is this apparently two disjoint or these 4 disjoint Lorentz transformations can be connected to each other by multiplying the appropriate Lorentz transformation matrix by either P or T or PT. So, we have the relation that is given by 39, 40 and 41. So, so far what we had done was started with the Lorentz transformation matrix, and assuming that the parameter that brings in this transformation can be varied continuously, then we have the rotational matrix corresponding to rotation and boost. But there also exist transformations. Those are not continuous transformation, and they are parity and time reversal transformations. They are the discrete transformation of the full Lorentz group L. So, so far the number of transformations that we have talked about turned out to be 4, and they are basically geometric in nature, but there also exists another discrete transformation that is called charge conjugation transformation. And when you consider this set altogether, we have 3 discrete transformations and 2 continuous transformations. And application of them actually is bound to change the observables if they are in the vectorial representation or tensorial representation or otherwise. That is the whole purpose of the whole discourse that we have initiated. Now, before we go on to do that, I would like to change the conventions a little. The Minkowski metric that we have defined by eta in the previous lectures will be identified with the metric tensor in flat space J mu nu. The signature of the metric that we consider to be +1, which is pretty popular among the practitioners of GR, that is theory, we will just change it to -2, and we introduce the definitions for the covariant and contravariant vectors, where the contravariant vector has a index on top, the time and space coordinates are all positive, and covariant one, that is obtained by lowering the index of the contravariant vector with a metric tensor, has temporal component to be positive and spatial component to be having is negative relative to the contravariant one. And lastly, there will appear Greek indices and Latin indices as we go along. The Greek indices will take values from 0 to 3 and the Latin ones will take values between 1 to 3. The improper Lorentz transformations or orthochronous improper Lorentz transformation, the parity inversion in this new system of conventions are almost same as that of the old convention, except for the fact that if you multiply the old parity reversal operator P with a -1, you get to the new one. So, P has its entries or diagonal entries as +1, -1, -1, -1, and the time reversal invariance matrix or transformation is now -1 and rest of them are +1 on the diagonal sides. Off diagonal elements are 0 for both the cases. This is the departure that from what we already had seen earlier. So, now what happens? There are unitary transformation matrices called as U of P and U of T to define the parity transformation and time reversal transformation, and their action on a quantity phi of x, when phi is a scalar, is given by phi of P inverse x, and time reversal transformation on the same object phi of x given by T inverse of x. What we have not covered, but can be done easily, that says that if we operate parity inversion operation on a spatial part of an object twice, what we should get back is identity. What it means is, I first change the coordinate x to -x, then again on -x I operate parity transformation, reversal transformation. So, I should get back what I started with. So, acting parity twice on this particular object gives me back the identity matrix. So, I can formally say that my p square is actually equal to 1 at the operator level, and so it follows from there that P is identical to P inverse, because if I multiply both sides by P, then I get on the right side 1 and the left side P square, and the same argument follows about time reversal transformation, and the conclusion that comes up is P and T are their own inverse. So, in equation 44, wherever there is a P inverse, you can replace it by P, and wherever there is a T inverse, curly T inverse can be replaced by a curly T. Thank you.